All right. Oh, no, I'm never going to be able to get back to that. Yeah, I am. Okay. So I'm going to look at classwork, and we're going to look at families of functions. Actually, just to start off, you remember families of functions. These are families of functions. Y equals mx plus b is the family of linear functions. Y equals ab to the x. Okay. Let's see what else I can come up with. This one's sort of a dead giveaway. Said with a sinus sounding. Yeah, that's a sinusoidal family of functions. I think you also did like polynomial, well, we could just say this, right? That's not quite polynomial, but more specifically,
that's a
quadratic, right? So these are all families of functions, and these families of functions all depend on the parameters, a and b and m, whatever they are, changes how the function's shape looks, but they're all in the same family. They all have very similar behaviors, right? So all lines don't look exactly alike, but they have similar traits, like constant rates of change and y-intercepts. Is that all right? So we're going to use calculus to look at families of functions. In other words, we're going to use calculus to look at like functions that have parameters in them. And it's just a generalization of everything that we've done so far. So I'm not going to teach you anything new. But the hard part is that you have to be okay with parameters and not numbers. And that can be tough sometimes for students to get accustomed to. So if we take a look, I think 10, 11, 12 sort of all go together, I think. So I don't even know what that is up there. All right, so if we look at 10, ax plus b over x is a family of some type of function. I actually don't know what kind of function that is. The ax looks like linear, but the b over x? What do we do? What is that called? The
rational function?
Like a rational? So it looks like a combination of like a linear and rational, something over x. So I got to figure out what I can tell about this family of functions. So I know that it's equal to ax plus b over x, and the question asks, what are the critical points? All right, critical points. Jack, you want to talk? How'd you get that? Come on, you're right.
The derivative would be a plus. Yeah, just b, right? No, b.
Now, I thought I had a room full of qualified differentiators. You could do the quotient rule, or can't you do that? Okay, so, or you could use the quotient rule, I don't care what, but what do we end up with?
Negative b
x to the negative 2.
Alright, so negative bx to the negative 2. I'm going to write it like this. Is that okay?
Yeah, sure.
Okay, so,
How does the quotient rule doesn't? Oh, it does.
just remember, and this is important, well, tell me can you tell me what you figured out in that, 2 seconds when you didn't?
I just forgot to do the over row square.
Oh, really? Oh, that's not what I thought you forgot.
Ways.
You can. I was hoping that you were, here's what I was hoping. I was hoping you were going to say, Betsy, that you forgot that the derivative of b was 0 when you did low d high.
That's why I just thought it was b.
Right. So the derivative of b is 0. And you have to remember that if you're going to use the quotient rule. So look, you're right, Jack. One of the critical points is when x equals 0. Right? Why? It's when it's undefined. But I have news for you. Go back to the original function. It was undefined there anyhow. So we don't call it a critical point because it's not in the domain of the function. It's an interesting point, though. So I like that. It's an interesting point.
By definition.
A equals B over X squared.
All right, hold on. Let me catch up with you. So A equals B over X squared. Yeah, keep going.
So times X squared, so A X squared equals 2.
Keep going. X equals B over A, take the square root, plus or minus. So those are my critical points for this function. Plus or minus the square root of B over A. Go ahead.
I thought it had something to do with compound formula, but that's like not. It's not square.
Not the same like B and A. I can understand what you might be thinking. Not the same B and A. Alright, so... Alright, 11 and 12 might be interesting, but I guess maybe I want to ask you some more questions. Let's assume that A and B are positive. Alright, I think, does it say that, or does it say that in 11? 11 and 12. Alright, so let's assume that they are both positive. Is there any way of telling if this is a minimum or a maximum? Which of these are mins and which are maxes? Asa?
Find what the zero is when in the second derivative.
Alright, so you're thinking the second derivative test might be useful. We can plug it in to find out if it's a min or max. Yeah, let's do that, because that was a good suggestion. Alright, second derivative of A, I got that one. Don't sweat it. That's 0.
Can you just write it to the 1 hand?
For x squared?
No. It's negative
For-
x B over. Oh, never mind.
So the derivative of A is 0, then
B to the x to the fourth.
negative, I think it's B,
Times 2x.
X to the fourth.
negative 2b
Yeah, the negative 2.
Oh, true.
over x
True,
cubed.
true. Yeah.
If you do low d high minus high d low over low squared, you can factor out an x in the top, and it reduces. If you don't like that, I just think about it as b x to the negative 2. Negative 2 out in front, x to the negative 3. Is that okay?
So it would be negative.
Say that again.
So it would be negative.
Oh, it would be positive? Okay. Derek said I didn't do that carefully. I agree. Thanks.
Wait, sorry, can you explain it again how you got that?
You tell me.
2b over
You tell me which way you want to do it. I don't care.
quotient
Quotient rule? Fine. Low,
x squared.
d high, minus high,
B.
well, negative b. D low,
2x.
all over,
So why isn't it?
So if
Times
you-
2x.
Factor out an x.
No, you take out
right,
an
x and x to the fourth.
I see. You take out an x out of the top and the bottom.
Mm-hmm. Okay.
So it's like
You're going to notice something, whether you like it or not. I'm going to actually spend less and less time actually talking about derivatives.
oh, come on,
Right.
it's so fun though.
Yeah, but wasn't that the whole point of chapter 3? Right?
Yeah.
All of chapter 3 was to talk about derivatives, so we don't have to focus on taking derivatives this chapter. Right? So you might not like it, and I can live with that. Alright, so let's see. You said, why don't you do the second derivative and then plug these points into the second derivative? So what happens if we take the positive root b over a and plug it in? What are we plugging it in for? For x. So that's going to be 2b over root b over a cubed. Alright, well, b and a are positive, so b divided by a is positive. Take the square root of it, positive, cube it, and b is positive, so positive divided by positive, that's going to be positive, which means right there the function is concave up. So x equals root b over a is a minimum, since the second derivative of root b over a is positive. Is that okay? Go ahead.
Alright.
You
Do you
sure?
have to do the negative now?
Yeah, we do. So we need to take this whole thing and plug in negative b over a. So we get 2b over the square root, negative the square root of b over a cubed. Alright, so b is positive, b over a is positive, the square root of b over a, positive. Negative, if we take a negative number and cube it, you get a negative. Because negative times a negative, right? Cubing it, you're going to get a negative. So it's positive divided by negative. We're going to get a negative, which means the function there is concave down. So x equals negative b over a is a max, since the second derivative is negative. Do you see how that's a little harder?
Yes.
Same thing, but harder, right? I mean, it's not like I'm teaching you anything new, but conceptually, I think it's more challenging. I want to do the first derivative test too, but I want to ask if there are questions. No? Is it Asa?
So you can tell if it's max if it's concave down because it's like sloping like that, and for a minimum it's like vice versa. Like
Right. If you know that it's concave down, it's got to look something like that.
Yeah.
But it's the combination of being concave down and a critical point.
Mm-hmm.
Just because it's concave down doesn't mean anything, but because it's concave down and a critical point, that means it's going to have to be a max.
Okay, thanks.
Okay. Tom?
In terms of plugging in the answer that we got for the first derivative into the second derivative, and determining whether it's concave up or down.
Yeah.
With the test, if it doesn't matter. I mean, is one test more accurate than the other? Like, is this more accurate than doing the derivative test? Or?
No. Let's do it, and then you can tell me whether or not you thought one was easier than the other. Is that fair enough? Okay. So if we were to do the first derivative test, we would have had negative root b over a and positive root b over a. That would have divided our function up into zones. Okay, so... Oh, and I actually know something interesting is going on at 0. I know it's not a critical point, but the function's undefined there, so something could happen. All right. What's the immediate problem? Like, I'm going to ask you to pick something greater than root b over a. All right, so you guys actually first. Was anyone I'm actually impressed. Was anyone ready to give up when I said pick something greater than 2 parameters when you don't even know what they are? Yeah, thanks. That's what I was looking for. All right, now, Zach said try b over a. Isn't b over a greater than the square root of b over a? So,
You may not know that.
Why?
Because if that number is less than 1, then your actual square
Yeah.
root is 1.
Yeah. So if it's greater than 1, it's true that the square root's less, but if it's less than 1, the square root actually is bigger. The square root of 1/2 is bigger than 1/2. So that was a nice thought. Derek said try root b over a plus 1. That's got to be bigger, right? Now, I'm going to go back to the derivative, just to remind you the derivative is a minus b over x squared. I'm a little squeamish about taking root b over a plus 1 and needing to square it. Right? That's going to get ugly, and I'm going to have to figure out whether this is positive or negative. So it's a good idea. I have a better idea, though. Am I supposed to tell you, or are you going to tell me? You want me to tell you? Okay. I actually think a number that's bigger is root 2b over a.
Yeah. I agree.
I think that works no matter what. Is that all right?
Yes.
For real? Okay. So it's like along Derek's lines, but instead of adding, I'm multiplying. I'm doubling the top. All right, so let's see what happens if we plug that in. Now, remember when you were bellyaching about having to plug 1/2 into the number line? Right? Because it was a fraction? Come on. Wasn't that yesterday?
Yes.
Yeah, okay. Do you agree that this is even more of a pain? Yeah. Okay. So minus b over... What happens when you square a square root? 2b over a. So we get a minus... ab over 2b. So what cancels? The b's. What's a minus a over 2?
No, it isn't. It's just
Wouldn't you have to multiply the A?
no. You can distribute the A out. So it's
A squared,
multiplied.
yeah.
It's A multiplied by 1 minus 1/2.
But don't you only have to see if it's positive or negative?
Well, weren't we saying A is positive from 11 and 12?
A is the same number, and A minus
A is positive.
divided by
You can just factor
Yeah,
out
okay.
A.
All right, factor out an A, and you get 1 minus half. So what is it?
So it's just A 1/2 A.
1/2 A. A minus A halves? Well, A halves is just another way to say 1/2 A. So what's A minus a half of A? 1/2 A. That's positive. And we only did one interval? Are you kidding me? All right, so you understand?
It's just tedious. It's not close.
All right, so I love what Will just said. Say it loud so everyone can hear you.
I'd rather use the second derivative test.
Will's saying the second derivative test actually is sort of nice. Now, it's nice if the second derivative is nice. Okay? Sometimes the second derivative can get pretty ugly pretty fast. All right, let's have a little fortitude because I want to show you a couple more things about how to pick clever intervals. Go ahead, Tali.
So with the second derivative test, I thought you could only use that to determine the closing function.
Nope. We've said it a couple times. There are actually two ways to use it. The first way is the second derivative can find possible points of inflection. The second derivative is good at finding those.
Right.
But you can use the second derivative to test your critical points to see if they're mins or maxes. So there's a total difference between the second derivative test and using the second derivative to find points of inflection. All right? Just like there's a difference between the first derivative test and using the first derivative to find critical points. One is finding them, the other is seeing what they are. All right? So the first and second derivative test are both ways of seeing if the critical points are mins or maxes. Is that okay? And I know it sounds like we're saying the same exact thing, but we're not. All right. Let's see how we do. If I want a number between 0 and root b over a, and can I just say, I mean, it's not that I was clever. Someone else was clever and showed me that trick, right? I'm just passing it along to you.
No.
So it's not like I'm super smart. It's just I've been doing this for however many years, right? So that's how I know it. So can anyone sort of be clever and pick a number that's between root b over 2a? If we double the denominator, it's going to make it smaller. Is that okay? Mm-hmm. All right. So if we were to plug in root b over 2a, this time we'd get a minus b over 2a, a minus 2ab over b. So what cancels again? B. So we get a minus 2a. Well, if you have a number and you subtract double that number, if the number's positive, it's going to be negative. So all that work, and we can now say that this is going to be a minimum because the function is decreasing and then increasing. Will would say, hey, guess what? We did that with the second derivative test in a lot less time and a lot less stress. Right? Can you see how you could pick these intervals?
Yes.
Is that all right?
Would it just be like negative 2b over a and like negative, like square root 2b over negative 1? Negative 2a?
Negative root b over 2a.
Yeah.
Yeah. Is that what you said?
Yeah.
Maybe. I don't know if it's what... Okay. So do you understand how we're not doing anything different, but why it's harder? Because we're not dealing with numbers, right? Mm-hmm. All right. Oh, shoot. Here it is. Can we try finding some critical points here?
Oh, yeah.
I guess so.
Now, some of you, look, you can use the quotient rule, but you may very well want to just rewrite it. Derek, you want to do first derivative? 2AR to the... Derek, all right? All right, so if I want to find where the critical points are, let's see. Maybe rewrite it like this and set it equal to 0. Where's it undefined? 0. Hey, look at this. R is greater than 0. It doesn't, because it's not even... Totally, I agree. Zach said, look, it's undefined, but it wasn't going to work in the function anyhow. So it's not even really an interesting point at this point.
I have a question.
Yeah.
Can we, if we like take out 1 over r to the third?
All right, 1 over r cubed, and we're left with 2a.
Minus 3b over r. Would that be helpful at all or no?
Yeah, sure. So we know that r equals 0 is undefined, and we need to solve this for r.
So 2a equals 3b over r.
2AR equals 3b. All right, so r is equal to 3b over 2a. So you could imagine that's a critical point. Now, if we needed something bigger than 3b over 2a, what could we choose? Yeah, 6b over 2a, or otherwise known as 6b over 2a. Yeah, that's just what, 3b over a? Or you could do 2b over a, right? But, you know, Gabby's using that same strategy, just double the denominator. Something less? Wait, did I do that? 3b over 6a, or how about just 3b over 3a? What would 3b over 3 just be over a? Doesn't that look sort of simple? A little simpler? Right, and we could use those to plug in. Does that seem like a better option? Using the second derivative? Let's take a look. Let's see if, alright, so, second derivative. Zach, you want to do it?
It's -6AR -4 minus, or plus 12BR.
Okay, so I guess that looks like -6a over r to the 4th plus 12b over r to the 5th. And I have to plug in 3b of what? So if I want to, is this not going to happen? Maybe not. -6a, and then I have to plug in 3b over 2a into the denominator. And 12b, I have to plug in 3b over 2a. Well, okay, which do you want to do? All right.
No.
You just wait till tonight. You just wait. And then ask yourself if you weren't wishing we hadn't done a little more of this. All right, that's fine. I see where you're coming from. All right, so I would definitely not wait until Sunday night to start this homework. I would actually start it, if you can, tonight. Worst case scenario, tomorrow. But I think you're going to be a little overwhelmed, I think, if you wait, because you're going to forget some. Now, I will say this. The first 3 or 4 problems ask you to find, like, the equation of a line, the equation of a cosine function, the equation of an exponential function. Those are all questions that I could have asked you last year or in Chapter 1 this year. So you should feel like the first 4 or 5 problems are a piece of cake. The next 2 or 3 problems are not. Okay? So if you come in with some tears in your eyes, I'll understand why. Have a great long weekend.
You too, Mr. Mail. See you later.
Thanks.